Hello everyone, I hope all of you are doing great. So today in this lecture we are going to discuss about a very important concept from the chapter complex number, that is about the straight line. So I'm sure if I will talk a basic kind of a the different forms how to write the straight line and all about the straight line. So we used to study this particular chapter, that is the straight line and pair of a straight line, in the coordinate geometry itself. But today we are going to see how we can write the equation of a straight line on complex plane, that is basically using the Argand plane. So whatever we have seen till now, that was basically using the Cartesian coordinate system. I'm sure that you might have seen this expression, that is ax plus by plus c equal to 0. So this was the form of a straight line in a Cartesian coordinate system that we have seen. But today we are going to discuss, that is a straight line, how we are going to write the equation of a straight line on complex plane, that is on Argand plane. Complex number, in complex number we are going to discuss about equation of a straight line, joining two points. Let's suppose z1 and z2. So whatever we are going to discuss right now, that is not on a Cartesian coordinate system but on Argand plane. So equation of a straight line joining 2 points z1 and z2, and this z1 and z2 is the point in the Argand plane. So before jumping into the topic, let me draw Argand plane. So let's suppose this is the Argand plane and this is the line I'm talking about, and there are 2 points given, that is z1 and this is z2. So we have to basically write the particular equation of this straight line. So before jumping into the proof and writing how how we will get this one, so I'm just writing it, that is alpha z bar plus alpha bar z plus r equal to 0. So this will be the equation of a straight line on complex plane. So I'm sure you might be thinking that the point what I have considered here, z1 and z2, but nowhere I have written z1 and z2. But rest assured, we are going to prove this particular equation, and definitely will use this concept z1 and z2 only. But there is a particular important concept that you have to remember about this r. So if I will talk about this r, so this will be purely real. So this is purely real. I will prove this also, why this is purely real. So this is purely real, and later on you will get to know the particular expression what I have written it here is basically the same thing what we used to study in a straight line in a coordinate geometry, that is ax plus by plus c equal to 0. You don't have to worry at all. This is the same thing, but the expression is written in some other format, but the meaning is basically same only. So let's consider a general point z here on this line. Okay, so z can be here also, z can be in between z1 and z2 also, and z can be here also. So there is no restriction because z is a general point on this line, so z can be anywhere. So I'm considering z here. So consider the particular coordinate of z is x comma y. So this is the ordered pair form. Basically it is written z as a complex number lying on a particularly Argand plane, having the expression as x plus iota y. Similarly, this will be x1 comma y1, and this is as x2 comma y2. So there are few things that we have to understand before jumping into the proof, that what are the what are the important points we can conclude from the given expression. So first thing that we can understand from the given part, if I will talk about the argument, so definitely the argument of z minus z1. So basically this one I'm talking about, z minus z1 upon z1 minus z2. I'm sure we have seen this particular term, that is the argument, while discussing in the previous classes, that what is argument and how it is related, and more about the argument we have seen in, specifically if I will talk, then the angle between the lines. So we have seen about the complex slope also, and there are so many terms that we have seen. But here, that is the argument, this will be definitely either 0 or pi, depending upon the position of z, whether it is lying here, or it is lying between z1 and z2, or it is lying, before z2. So accordingly, we'll have the 0 and pi. But if argument of this particular complex number is 0 or pi, then definitely z minus z1 upon z1 minus z2 will be a real. So we can say here, like, if you want to talk about the real, then you can use it, or else you can just simply say the complex slope will be equal. That means z minus z1, z1 bar, z bar minus z1 bar, and z1 minus z2 upon z1 bar minus z2 bar. So this will be the expression, or if you will simplify this, you will have the similar expression. This is nothing but, this is like z minus z1 upon z1 minus z2 is equal to z1 bar minus z bar minus z1 bar, z1 bar minus z2 bar. So it simply means that the given particular complex number, this particular complex number is real, because z is equal to z bar. You can simply consider, if I am talking about x plus iota y is equal to x minus iota y, so this will get cancelled out and you will have y is equal to 0. So if y is equal to 0, that means it is purely real. So this is purely real. That is the reason we have considered the argument as 0 or pi. So I hope this part is pretty clear, and why we have done like this. So this term we generally use to say a complex slope, and definitely this is not the topic right now. So currently we are focusing on this particular equation, how it will come. So there is one more thing you can conclude from this particular diagram, that is the given z. This is the third point. The given z can be written as, passing through the point z1, you can consider z1 or z2, like I'm sure you might be knowing the complex number can be represented in the vectorial form also. So z is equal to basically z1 plus say lambda times of z1 minus z2, where lambda belongs to real. So this part must be clear if you have bit of idea about the vector algebra. So this also we can conclude from the given diagram. And apart from this, I'm coming to the main part. That is, I'm sure since we have seen the given point z, this particular given point z, z1 and z2 are collinear. So definitely area formed by these 3 points will be 0. So if I want to write, in determinant form, then I can simply write 1 upon 2 mod of x, x1, x2, y, y1, y2, 1, 1, 1 mod equal to 0, because points are collinear. So in order to introduce z, in order to introduce this z, z1 and z2, we are going to use the property of determinant. So simply we can write the above expression like, I am multiplying iota in the column 2, this particular column I am multiplying the every element of this particular column with iota, and in order to balance it out, I am writing it here, I like this. So 1 upon 2 iota and multiplying the given column with the iota. So let me rewrite this one. So the above expression can be written as 1 upon 2 iota mod, and this is x iota y, iota y1, iota y2, this is x1, this is x2, and this is 1, 1, 1, and mod is equal to 0. So using the property of determinant, we have written like this. Now the next step is pretty simple. Like I can write this x as 1 upon 2 iota and we can write x as z plus z bar by 2, and this is z1 plus z1 bar by 2. And similarly we can write this x2, this is z2 plus z2 bar by 2. And this iota y, I'm using the particularly property of determinant, that is I'm changing the column 2 plus column 1. So this will be basically x plus iota y, and x1 plus iota y1, x2 plus iota y2. So this is nothing but z, this is z1, and this is z2, and this is again 1 1 1 1 1 1, and mod this is equal to 0. Further I can take 1 by 2 common, so it will be 1 upon 4 iota, and this is mod, and this is z plus z bar z1, z1 plus z1 bar, this is z1, this is 1, this is z2 plus z2 bar, this is z2 and 1, and this mod equal to 0. So again we'll use the sort of property of determinant, that is addition property. So we can again write the above expression as simply I'm writing this one as z bar, z1 bar, z2 bar, z, z1, z2, 1 1 1, and this will be equal to 0. I'm sure everything is pretty clear till this particular step, how we came on this particular step. All right. So now I can see z bar, z1 bar, and all these things. So simply I'm just trying to expand the given determinant. So it will be z bar, z1 minus z2, and this will be plus z, and then again it will be z2 bar minus z1 bar, and further it will be written something like this. This is plus 1, and this is z1 bar z2 minus z1 z2 bar equal to 0. All right. So if coming to the point what we have started in the starting itself, the expression what we have written was something like this: alpha z bar plus alpha bar z plus r equal to 0, where I have mentioned that r will be completely real. So now we have to change the given expression, this particular expression what we have from the determinant value to something like this. So in order to do that, we are going to use few of the things, that is, since r is a completely real, so we have to focus on this one, that what is the nature of the given expression. So if let's suppose I'm saying the given expression as k, so this is z1 bar z2 minus z1 z2 bar. So definitely if I will take the conjugate, so basically k bar will be equal to nothing but z1 z2 bar minus z1 bar z2. So k bar is equal to z1 z2 bar minus z1 bar. So definitely k is nothing but minus k is equal to minus, because you can simply have this expression, that simply means k is purely imaginary, that simply means k is purely imaginary, purely imaginary. Now since this is purely imaginary, so if I will multiply the given expression by iota, then we'll have the purely real part, and since required this particular expression as purely real, so that I can replace this expression with the r, and our initial condition will be satisfied. So this is nothing but now I can multiply the given, multiplying the given expression with the iota. So multiplying the given expression with the iota. So this will be z bar iota z1 minus z2, and I'm taking the minus common here. So this is iota z1 bar minus z2 bar. This is z, and this is plus iota z1 bar z2 minus z1 z2 bar equal to 0. So definitely now I can say, let's suppose if I am saying this as alpha, so this expression is nothing but alpha bar, that is the conjugate of alpha, and this is purely real now. This is purely real, and if this is purely real, that simply means, if this is purely real, that simply means I'm replacing the given expression with the r. So this will be z bar alpha plus alpha bar z plus r equal to 0, where you can say alpha is iota z1 minus z2, then definitely alpha bar or conjugate of alpha will be minus iota z1 bar minus z2 bar, and r is purely real. So I hope this part is pretty clear, and you have understood how did we write this particular expression as equation of a straight line, this equation of a straight line, this straight line joining the point z1 and z2. So this is all about today's lecture, and we'll see how to write the equation of circle and diametrically form of a circle in a on complex plane. So that is for the another lecture. So thank you so much. Have a great time ahead. We'll continue in the next lecture. Thank you so much.